Welcome to Section 6, Global Independence D-Separation. Back to our sit-in practice example, the COVID example with 12 variables. We said just assume that the true joint distribution P of the random variable satisfies the previously stated independencies, the IP that was stated. And the first question was whether the above graph is an IMAP for P, meaning that P factorizes according to the above graph, and we saw that the answer is yes. Now here's another question. Does the factorization, according to this graph, impose any independence in addition to the previously stated ones? Okay. So, and what do I mean by that? So all the previously stated independencies were local, like fever condition on its parent was independent of its non-descendants, right? And cough condition on its parent COVID was independent of its non-descendants, and so on. But what about, say, allergy and COVID? Allergy and COVID, shown in orange here, are they independent? How can we answer such a question? This exercise is asking you to show that they're actually independent by working on this factorized joint probability distribution, similar to the previous sections. So after showing that they're independent, then it's asking whether this independence is included in the local independencies, ILG. And the answer is no, because if we go back to the slide that we discussed these local independencies, we saw that A is, the allergy is independent of other variables, condition on S, and C is independent of other variables, COVID, condition on M and D. So we don't have any direct independence of A and C without being conditioned on anything. So you may say that, well, maybe I can conclude by playing around with these equations that, well, from these two or from other conditional independencies, that allergy and COVID are actually independent from each other. Well, that is a different story. The question is whether it's included here or not, and the answer is no. So then the next question is, how can we find and discuss such independencies? So let's go into the details. Consider this joint probability distribution over x1 to x4 and assume that it's factorized in this way. I can draw the corresponding Bayesian network graph. So just from each node, each variable to its parent, and we will get this simple path. And I can get the corresponding local independencies, ILG. X1 and X2 don't have any non-descendants. X3 condition on its parent X2 will be independent of its non-descendant X1. And X4 condition on its parent X3 will be independent of its non-descendants X1 and X2. So I will have these conditional independencies, but are these the only conditional independencies? And I guess the answer is clear. It's no. We just saw one example there. But for this particular graph, what will the answer be? For example, what if we condition x4 not on its parent, but on some other node, say x2, which is here? What can we say about this case? Okay, let's do the math here. I want to investigate whether x4 and x1 condition on x2, so x4, x1 condition on x2, they can become independent, meaning that the probability of x4, x1 condition on x2 can be written as x4 condition on x2 times x1 condition on x2. Okay, let's go through it. So by definition, this conditional probability can be written as the nominator divided by the condition part. And I want to use this factorization. So for that, I need to have x1 to x4 on the left part. Here I just have 4, 2, 1. I'm missing x3, so I will just add it here, but I cannot just add it there. So I need to sum the term over x3, marginalizing it. Okay, so by doing that, then I can factorize it. So I will have this term, and then I will do a trick here. I'm having this x2 condition on x1. At the end, I need x1 condition on x2. So I will just reverse the direction by replacing these two terms by this, just based on the Bayes rule. Okay, so we'll end up here. Now, look at this part. x4 condition on x3, x3 condition on x2, and then times x2. This is basically the sub-Bayesian network here. So if I ask you to write down the joint probability distribution for this part, you can just write it like this, right? And if you don't want to do it, if you want to do it algebraically, you can just check that, okay, this two part, P of x4 condition on x3 and x3 condition on x2, the two together, because of the independencies, the conditional independencies that the factorization are imposing, this is equal to P of x4 and x3 condition on x2, and then if you multiply it by x2, then you will just get the joint of the three of them here. Now, marginalizing x3 out, you will end up at P of x4 and x2. You see, just the role of x3 was really to just use it here. It didn't play any other role, and then it is marginalized out again. And then, of course, dividing these two, then I will get the conditional probability, x4 condition on x2. Okay, so we'll have this, and therefore I can conclude that x4 is independent of x1, condition on x2. Okay, so what just happened? This is not a local conditional independence. It is not captured by ILG because x4 is not being dependent on its parent. Okay. It is a global independence. That's what we call it. The global independencies result directly from the factorization. Okay, so still we use the factorization and we ended up in this independence. And we will later denote them by I of G. So here we had L standing for local, but here we have the full IG. Okay, and in this case, x4 is independent of x1 condition on x2 belongs to IG. Okay, good. Now, this type of conditional independence holds for a general graph including nodes V1 and V2. So just look at what we had here. It was x4, x1, and then somewhere in between, it was a directed path. We had x2 being conditioned on or observed. Okay, let's just simply generalize it. So V1, V2, there's a directed path, or as we will see, actually it doesn't need to be a directed path in this dotted part, dashed lines. Okay, this part of the graph doesn't matter. The only thing that matters is this. There's in between, there is a y linked to z, linked to x, and z is observed. Okay, so we have v1 to v2 connected by some path, doesn't matter what type of path, but become disconnected if node z is removed. Okay, so this is what we see here. And then I want to show that P of V1 and V2 condition on Z, what will happen here. Okay, I want to investigate the possibility. So whether I can write it down separately or not. Similar to the previous case, just a mild extension. So using the ideas that we had in the previous slide, I can write, again, I will write it down as the nominator altogether divided by P of Z, and then I will use the factorization. So I say this, V1, Z, and V2. I will just put all the other nodes here, like X, Y, and everything else, and marginalize them out. So over all V, other than these three, and then I will use the factorization, the Bayesian net factorization. So basically every node condition on its parent. Okay, so this part shouldn't be new to you. And then I'm multiplying it by P of Z divided by P of Z. So this is somehow resembling the Bayes rule that we used in the previous slide. Okay, now what I will do is I will have P of Z together with this part of the graph, the first part V1. So this is the subgraph V1. You see it doesn't include Z. V2 includes Z. Okay, and I will put that together with the first part. The second part, I will just leave it there. So I just decompose the factorization, nothing special here. Now this second part, I just divided it into two groups, V1 and V2. This second part is quite easy. So what do I have? I'm multiplying the probability of each node condition on its parent for all of the nodes in this part, V2, okay? And it's not difficult to see that this will be just the joint probability of all of the nodes here, okay? Every node condition on its parent, including Z. Z condition on its parent is Y, and then I will have the full graph here, P of V2. Now what about the other part? For this one, I have every node condition on its parent is included, but then for X, I have it conditioned on Z. Now, if I want Z to be here as well, like P of V1 and Z, I need to have P of Z. That's why we multiplied. We did this multiplication, okay? So I will have P of V1 and Z. So again, these are the Bayes rule factorization for these subgraphs. So we'll have these two terms, and I'm marginalizing out the remaining terms. So all of the ones in V1 other than V in this set V1 other than the node V1 will be marginalized out, and the same for V2. For V2, just note that I'm marginalizing out every node other than Z and V2. So I will have only these two left, and then I'm using the divisions to get the conditional ones. Okay, so what happened? We see that this has been factorized into these two terms, so I can conclude that V1 becomes independent of V2 condition on Z. Now we can do this, the same process for these types of graphs as well. Like when V1 and V2 are linked in this way. Of course, this is just the opposite of the other one, so this is not surprising, but this one also holds when Z has both of the directions outgoing. An intuitive way to think about all this is that the node Z is blocking information flow between nodes V1 and V2. For example, in the first one here, you can think of V2 sending information to V1, but then node Z is blocking it here. And similarly, in the second one, V1 is sending information to V2, node Z is blocking it. In the third case, it's like Z is the common source of information for both V1 and V2, but now that it's blocked, there's no common source, and the two are independent of each other. What about this other case where node Z is the common child of both X and Y, which is also known as the V structure, because if I draw Z here a little bit lower, then it looks like a V letter. Well, in this case, it's impossible to break the joint probability distribution into two corresponding components, G1 and G2, which only overlap in Z. And this was the core idea of our proof here. Now, we cannot do that here because if I write down the conditional probability of V1 and V2 condition on Z, then at some point I will get to this conditional probability of P of Z given X and Y, and I cannot decompose it to, for example, P of Z given X and P of Z given Y. And I cannot do the consequent parts of the proof like the previous ones. So this doesn't work. V1 and V2 condition on Z are not in general independent. However, if we don't condition on Z and include Z in the summation, then the two will become independent. Back to our intuitive way of looking at this, the node Z here is like a sink. V1 is sending information, V2 is also sending information, and I have the sink here Z. Now if I block the sink, the information from V1 will not be drained into Z, it will get to V2 and vice versa. So in this case, they're actually dependent. But if I don't block Z, then the information from V1 will just, all of it will go into Z, and V2 will go to Z, so they don't pass to the other side, and they will become independent. This is only a way of looking at it that may perhaps simplify the understanding. It's no rigorous math. So, back to our problem. Now, if we don't condition on Z, what will happen? Can we show that the two v1 and v2 will become independent? Okay, so if I have p of v1 and v2 not conditioned on z, I can do the factorization after including all of the variables. I'm marginalizing them out, and then I can just do the Bayesian network factorization, and then I will separate some terms out. So I will keep v here for all of the set v1. So I will have all of this subgraph in this part, all of the second subgraph in this part, and for z I will have p of z condition on x and y. But this time it's the summation includes z. Okay, so I'm marginalizing it out. Now, what can I do is that, you see, from here to here, I will just do the summation, not because none of these two terms will have the summation over z, because neither x nor y, they have the parents, they have z as their parents, so it doesn't show up in any of them. So I can just put the not z here, and then I will only have it here, so I can put the summation over z on this last term. Now, of course, this will be 1. It's summed over the left part of the conditioning. Okay, so this will be 1, this will be p of v2, this will be p of v1, marginalizing it out for every term except for v1 and v2, and z. Well, of course, it doesn't even matter if I include z here or not, and therefore everything will be out, and I will be left with v1 and v2. So p of v1 in the first one, p of v2 in the second, and hence I will conclude that the two are independent. Okay, what happened here? So when I have a V structure, if I don't have Z observed, I will just have V1 and V2 being independent. I don't need to make it condition on Z. Okay? When I condition it, it's actually the other way around. I cannot conclude that they are independent. Now, note that the conclusion does not hold if Z had an observed descendant, like Z prime. Why? Because then Z would appear in both P of ZX condition on X and Y, okay? Z condition on X and Y as before, but also I would have this additional term, P of Z prime condition on Z, okay? So when I'm writing down P of Z, then I will have this term, but when I'm writing down P of Z prime, I will have also this term. And this cannot be marginalized out from the summation. Okay? Now, what did we learn? In all of the cases, there are two nodes V1 and V2. We're given some observed variables, like Z here. Either information flows between them, meaning that they can be dependent, or information flow is blocked, meaning that they are globally, conditionally independent. And for example, we had this case. Here, we saw that Z is blocking information from V1 and V2, whereas here, we say that information flows. Okay? Now, the information flow, okay, again, this is just for an intuitive term I'm using here. It's not mathematically defined or anything, just to help you to grasp the idea. We'll make everything rigorous shortly. The information flow between two nodes is actually a trail connecting them, which is active if information flows and inactive if it is blocked. Okay, that is what I really mean by information flow. And what is a trail? It's basically a walk here without a cycle, if you know it from graph theory. So a sequence of consecutively connected nodes x1 to xn in a graph is called a trail, where x, y implies that x and y are connected. The direction doesn't matter. Okay, so here v1 to v2, it didn't matter, like here whether the link direction is in this way or the other way or in any way. So the trail, the directions don't matter. Now, okay, so we saw how we're linking our intuition about information flow to whether they are the variables of interest are independent or not. Now the question is, how can we determine whether a trail is active or inactive? Okay, so we have seen three fundamental structures that block information flow, meaning that it's inactive trail, and they result in global conditional independence. So one of them was this: when we have y going to z going to x and z was observed. I'm no longer making them red following the convention. The red was just to help you to make it more like emphasized. So in this case, we say that yes, y and x are independent condition on z, and this belongs to the global conditional independencies. This is known as indirect causal or evidential effect, right? So why assume that these links are causal? They don't mean that. We saw that they have nothing to do with causality. They're just representing a way of factorization. But like if you think of them in that way, sometimes they can overlap the two meanings. Then you see y is like indirectly causing x via z, and then once you block z, once you know z, then it doesn't matter anymore. Okay, so that should give you the intuition. The other one was, and of course this can be both ways, either from x to y or y to z, y to x. The other one, if you still want to think about that causality thing, is a common cause, meaning that z is causing both x and y. And once we know z, then the two will become independent. Okay? So, because this is the only thing that matters. That's how it's causing the two. Again, it's only the intuition. Mathematically, we showed these, at least the first one. Now, what about the V structure? This one, if we don't condition it, then they will become independent, x and y. Okay? Now, inactive trail, global conditional independence. So all of these are inactive. This is blocked. Blocked, and a V structure by default is blocked unless Z is observed. Consequently, the structures that do not block information flow or are equivalently an active trail are when we do not block the node Z, in this case, the indirect causal evidential effect or the common cause case, and we do block node Z in the V structure case, or we block or observe one of its descendants. In all these cases, we have an active trail, which implies that we don't have a global conditional independence in the graph. Okay, see it in practice, interpretation of active trails. So getting back to our COVID example with this graph, the known graph, we are investigating whether a given trail, fever, flu, cough, is active or not. Okay, so this trail fits into the common cause case, right? So information will flow, and it's an active trail if nothing is observed, which is this case. Okay, so we have active trail. And the story here is that a person with fever, okay, gives us some information about that person having flu or cough, or whether the person is coughing. So if I know a person has fever, it may make it more likely that the person has flu or he's coughing. Okay. Now, however, if I observe flu, okay, then it will be blocked and the trail will become inactive. Because in this case, if I know that the person has flu, I know the cause, the common cause, then it doesn't matter if I know that the person has fever or not. The probability of having fever will become independent of the probability of coughing. Another example, this time the trail is from flu, fever to COVID. It's a V structure, so by default, we know that it's an inactive trail. No information flows, which is in this case. There is no observed node. And what is the story here? Well, if I know a person has flu, can I conclude that the person has COVID or does not have COVID? No. In general, it's independent, right? But then once I observe something, if I know that the person now has fever, then in this case, if you tell me that the person does not have flu, well, I can I will ask, where is the fever coming from then? Okay, so it makes the person more likely to be infected with COVID and the other way around. Okay, so this time the trail becomes active because this node in the V structure is observed. Good. Now we want to make things more formal. Definition, active trail. Let Z be the set of observed variables, and we say a trail x1 to xn in G is active given Z if, so for any V structure, we know that either xi or one of its descendants are in Z, and no other node along the trail is in Z. So no other node is observed. So going back to our fundamentals here, you see that all of these are active trails. So you see that only for the V structures, we should have these nodes or the descendants being observed, but for the other ones, nothing should be observed. And that is the definition of an active trail. Okay. Now, a trail that is not active, we define it to be inactive. And to make it simple, you don't need to investigate it each time. A trail of just two variables, so x and y being linked to each other, we consider it as active. So here, mask and COVID are active. It's an active trail. Okay, a recall not from the past material, but something to help you memorize this whole active inactive trail. It may be helpful. If you're given a trail, okay, now if you put all of the nodes on a horizontal line initially, and then what you would do is to move up the common causes node, like here x3, and then move down the V structures, like here x6 and x8. Then intuitively, you may think of it as like x3, these common causes are source of, say, for example, information. They're like pushing down information. And then these V structures are the sinks. Okay. Now, if you want the whole thing to be active, like for information to flow, none of these nodes should be observed. Okay. You should not block any of them. Only the sinks, they may and they actually have to be observed. They should be blocked. Okay. So like, so that, for example, information doesn't just disappear here, it can move, it gets here and then it can move to the other node. Like, again, it's just, maybe it can be helpful to you to memorize this, okay? Now that is the story with active trail. Anything by this happening, like if the source of the information flow or somewhere here in the middle of the path is observed or blocked, per se, then of course it becomes inactive, okay? Good. Another example, so consider here we have flu, fever, COVID, difficulty breathing, and assume that nothing is observed. Now, is this an active or inactive trail? We have a V structure, nothing is observed, so of course it's inactive. Another example, same trail, but then this time drug is observed. Okay, so it's one of the descendants of the V structure, so of course it is active this time. Now, what if both COVID and drug were observed? Okay, this time, yes, this V structure is active, but then look at this one, the common cause. This is observed as well, and this is making the whole trail inactive. Good. So back to our definition, active trail and inactive trail. Now, in order to have global conditional independence, all trails must be inactive. Okay, if any of them is active, then information will flow and they will not be independent. And is there a proof for this? Yes. Proposition inactivity implies independence. So given observed variable z, if there is no active trail between the nodes x and y, here there are single nodes, in the graph G, then x and y are independent given z under any probability distribution that factorizes according to G. Another example, we want to see whether flu and difficulty breathing, here flu and difficulty breathing, are independent given cough. Okay, now for that we need to show, if it's going to be independent, we need to show that all the trails between them are blocked. So one of the trails is this one, okay, and then another one is here, and then another one is this. We need to investigate all three of them. So the first one is this. Is this active or inactive? Well, it's inactive because here the V structure is not observed, the fever, the node fever, or its descendant. Okay, so it's inactive. Good, this is blocking information. The other one is this. We have this trail here, and cough is observed. Okay, so this is of course blocked as well because this is not a V structure and it is observed. Good. What about the last one? So this is the trail. Now it is a V structure, but it is observed. Okay, so then this becomes active actually. So even though these two were inactive, it was blocked from there, but information of course can flow from here, again given that intuitive reasoning. And flu and difficulty breathing given cough does not belong to the set of global independencies of this graph. Okay, now so inactive trails provide us with global conditional independence between two single variables. What about if we want to determine groups of variables, whether they are independent or not? And this is, so it's of course a generalization of the previous single variable case, but this is like the ultimate tool for determining independence. And that's called D-separation, standing for dependence separation. Now in a graph G, two sets of nodes X and Y, we say that they are D-separated given the set Z, and we can denote it by this notation here, D dash separate, SEPG, and then X, Y, condition on Z. When do we say so? We said if there is no active trail between any node in X, in this set X, and any node in this set Y. It's quite, I would say, straightforward generalization of the previous case. See it in practice. So imagine that you are given this set X, so these green ones here, you want to see whether they are independent from the orange ones here, so season flu, allergy, congestion from mass COVID, social distancing, difficulty breathing, and ventilation. Okay, now and then first case, you see like that the ones on the left, it's more like flu based, and the ones on the right, it's more COVID based. First case, we don't have any observed nodes, and what are the trails connecting the two? So it's this, in both cases, it's these pink ones. And well, all of them are a V structure, and none of the nodes are observed, so it's definitely blocked. Okay, so here it is. So in this case, it's blocked. But if now we assume that fever is observed, okay, then definitely information will flow between COVID and flu from fever here. And therefore, in this case, they are not separated. So if we know the person has fever, these two groups will not become independent. It's kind of the same reasoning why we said flu and COVID will become dependent if we know that the person has fever, right? So that's the same situation here. Now, that was with D-separation, but now we can get to the global independencies or global Markov compared to the local Markov independence. The set of independencies resulting from D-separation. Okay, so again, D-separation imposes some independencies. We define it as a set of global Markov independencies, IG, and here it is. So this is the formal definition for IG. We had it before, but here now we're formalizing the definition. So all these types of independencies, so they're like kind of any possibilities here that the D-separation can do. Now, linking IG to IP. Theorem: if a distribution P factorizes according to G, like it's G is an IMAP, then IG is a subset of IP. What does it mean? It means that all of these deseparation independencies that we can conclude from the graph, they are definitely included in IP. We don't need to check any of that. We don't need to write down the factorization or check and see if we can prove it or so. Here it is. Okay, so namely, if P factorizes according to G, it satisfies all global independencies imposed by the D-separation. So the distribution of a Bayesian network satisfies all of the global independencies imposed by the BN structure. Okay, because that's how we define a Bayesian. A Bayesian network is a structure, remember, and a probability distribution P that satisfies, that can be factorized according to the structure. So therefore, this is, of course, guaranteed. Now, note that ILG, the set of local independencies, it's a special case of this Markov, global Markov, okay? And why is that? So just note that, for example, here, if I want to say fever, the local independencies, what does it say? It says fever condition on its parent becomes independent of all of its non-descendants, okay? So if I want to do deseparation here, if I want to investigate it like this, then I would say fever, what are the trails that connect fever to its non-descendants? Say, for example, these ones, okay? Well, the only ones are via its parent, right? And the parent is conditional, it's observed. So this is not a V structure, so it's blocked, okay? So therefore, all of the ones that connects fever to the other ones, they are blocked, and information does not flow, it's inactive trail, and so on with any of the other non-descendants. So here it's not from its parent, it's actually from the descendant drug, right? If I want to get to the other non-descendants. But then this time it's a V structure, right? And it's not observed. It's the only condition on its flu in the local dependence. So therefore, these ones will also become independent, right? So you can see that the local independence becomes a special case of global Markov independence, of deseparation. Good. Now, if ILG is a subset of IP, for P always, just if you want to remember something, remember that table. So if ILG, the local independence of G, are included in IP, okay? Like, remember in the summary, we had the table, we checked whether the local independencies are satisfied, and we said it's IMAP. Then we can say that P factorizes according to G, we already knew that, but then what this one additionally says is that then IG, all of these are also included in IP. Okay, good. So, meaning that if the local independencies are satisfied by P, so are the global ones. And that's the main message of this section. Good. See it in practice. Back to our allergy COVID example, it says show that the distribution that factorizes according to the graph satisfies the independence that allergy is independent of COVID. Okay. Now just note that this conditional independence is a general term for both conditional, really conditional independence and independence. Okay. And then the next part was, is it captured in the local independences, ILG? So for the first part, how can we answer this? We have allergy and COVID. All trails that connect allergy and COVID to each other, they go through flu, right? Here, and either fever or cough. So for example, you can go from here, allergy, season, flu, fever, COVID. This is one trail. Another one is allergy, congestion, flu, fever. So you definitely have to go through flu. And then out of the other ones, you have to either go through from flu to cough to COVID, or flu to fever to COVID. Or like this, doesn't matter. So you have to go through flu and either of them. But then you see that both of them are a V structure, okay? And none of these nodes are observed, so it's just blocked. So both of them are blocked because these nodes, neither the descendant are observed. So basically all the trails between allergy and COVID are inactive, and therefore the two are independent. Okay, so that's the easy way to show this. Now, is this captured by ILG? No, it is a global independence not included in local independence set, again, because in the local independence ones, we had allergy, for example, condition on its parent, and so on. Okay. Now, deseparation captures them all. So we already had this part, the definition of IG, the theorem soundness, which is a distribution P factorizes according to G, then IG is a subset of IP. All of them are captured. So every deseparation results in a global independence that can be obtained from the factorization. What about the other way around? Is also every global independence captured by deseparation? And here note that I'm talking about all the independencies that follow from the factorization. So imagine that you have written the joint probability distribution and the factorization, and then you start playing around with it, like marginalizing out some terms or other tricks, and then you end up with independence. Okay. Now the question is, could we get it by deseparation? Does IG include all independencies imposed by G? And here's the answer. If X and Y are not deseparated given Z in G, okay, so if deseparation cannot capture it, then X and Y are dependent given Z in some distribution P that factorizes over G, and that is enough. Just even if even in one distribution P that factorizes according to G, then X and Y are dependent, then that means that from the factorization, I cannot in general conclude that the two are independent. Okay, so the answer here is yes. So this was the opposite part, showing it like from the other way around. So meaning that yes, deseparation can capture all of the global independencies that follow from the factorization. So if you play around with the factorization, you do your own tricks, and you end up with some independence, I could find it by deseparation. Okay, good. We'll later see that actually this sum here, some distribution P will exist that make X and Y dependent if they are not captured by the deseparation. We see that it's actually almost all distributions P. Okay. Now, proof. Okay, this is a part that often the proof of this proposition is skipped in the classes, left as a homework exercise or whatever, but we want to do it here, just a sketch. So let's go through it. We can do it. Just be patient with me. So how can I show this? So imagine I have X and Y, and we assume that they are not deseparated, okay? But if they are not deseparated, what does it mean? First of all, it means that X and Y are connected by some active trail U1 to UN, because otherwise they would be deseparated. So imagine this is the active trail. For simplicity, we're just making it a direct path. For other cases, you can try to do it yourself. So we have this direct path, but of course, each node also has these additional incoming or outgoing edges. Like here, I put S0, I use it to denote all the other nodes that are linked to X and so on. Okay, now I want to construct my distribution P that factorizes according to G, but where X and Y are dependent. So they're not deseparated. So this holds here, but still, even though that such a path exists, the two are dependent. So we are free to choose our CPDs. Okay, I can build my graph P whatever way I want. It's just that it should be factorized according to this. Now, how I choose my CPDs is as follows. I choose them so that these UIs are perfectly correlated, okay, with each other, but have zero correlation with all these other ones, S0 to Sn. I just want to get rid of them, okay? So meaning that P of UI condition on UI plus 1, its parent, and these other parents, Si, it's equal to P of UI condition on UI plus 1. So just they don't depend on them. So although they're linked, they don't depend. And between these two, so ui and ui plus 1, this is just the Dirac function, delta. It's the difference of them. So, and this is when delta of x is 0 for all values equal, so delta x is 0 for all x not equal to 0, and at 0 it's 1. So it's like 0, 0, 0, 1, 0, 0, 0, 0. It's like this form. So basically what it means that here is that P of ui conditional on its parents is equal to delta ui minus ui plus 1. And this will be always 0 unless ui and ui plus 1 are equal. That's what it means. Okay, good. Now, then we can show that what happens to x and y. P of x condition on y, we want to show that this is not dependent. If they were dependent, it would be equal to P of x, but we show that it's not. Okay, so P of x condition on y, how can I write this down? It will be P of x condition on u1, u1 condition on u2, and all the way condition on y, and then you can multiply it by y even, but you don't need to. And then we marginalize out all these intermediate variables, right? Okay, so summation over ui and si, we have done this trick before. P of x condition on the parents, every node condition on its parent, and of course I need also to multiply it by si, and then multiply it by, I'm taking out this last term here, P of un condition on the parents. Okay, so I have this. Now I will use this formula here. So I will turn them into delta. SI's will be ruled out. I will only have PSI here. But the thing is that PSI is standing here alone, so it will be this will be 1. Okay. Now also, so what will happen to this? This will be always 0 except for one case. When ui plus 1, un, u1, all of these are equal to each other, and they're equal to x and y. So this will be 0 unless x and y are equal. So I can just simplify it in this form. This is also 0 unless x and y are equal. And you can see that it depends on the value of y. So it's not equal to P of x. Okay, and that's an example. What did we do? We just constructed an example, a graph that where x and y are not separated. There's an active trail between them, but still x and y were dependent in a distribution P that factorized according to this. Here it did factorize. I used this factorization according to the graph. Okay, so if you see in a graph that two nodes are not separated, don't jump into the conclusion that they are also not dependent. They're independent in the original graph P that is factorized according to this. Great. Okay, to finalize this, so we had this global independence. This was our graph. We said that is it an IMAP? We showed that yes, it was, meaning that our distribution P was factorized accordingly. Does the factorization impose any independence in addition to the previously stated ones? And by the previously stated ones, I mean like ILG. Remember, we stated like 1 to 8 here, and the local ones. And the answer was yes. So G does impose other independence than ILG, but the distribution P that factorizes according to this satisfies also all of them. Okay. So allergy COVID, we know that they are based on this separation, they are independent. Well, the distribution P that factorizes according to this, that also satisfies this. Summary, what was the goal? Remember, you were given a data set here, and we wanted to find how we can, which of the factorizations work for it so that we can reduce the number of parameters. And we say for that, we can just write down the local independencies here, right? And then check which of them are included here. And we set the IMAPs, those that included were these three, and they were the IMAPs. And then we ended up with the minimal IMAPs, because these are the ones that if you really take out any of these edges, then you no longer will match this table. Okay, so we said go with the minimal IMAPs. And then the question is, Does P satisfy all independencies, P here is this, imposed by the minimal IMAPs, the global independencies? So for example, here I may have other independencies not included by this, local ones. Okay, and it's asking, does P satisfy all of them? Well, here it's just 3 nodes, it's just for illustration, but you can imagine you had a bigger one. And of course the answer is yes, because of the theorem that we saw here. Thanks for your attention.